Hey, chemistry. It's time to talk about metals. We're going to talk about the properties of metals and how they have those properties due to metallic bonding. These are the metals. As you can see on the periodic table, it is the vast majority of elements on the periodic table are metals. And so we're going to talk about what makes them metals, why there's so many metals. It all has to do with electrons. So let's talk about some of the properties of metals. So most metals are shiny and are usually silvery in color. The exceptions to that would be gold and copper. A couple others have kind of a yellowish tinge to it, but the vast majority are basically silver. They conduct electricity, and they have low specific heat values. That means they conduct heat. So you can add heat to one portion of it, and the heat moves rapidly through the entire piece of metal. Most metals are malleable and ductile, which basically means they can be bent and twisted and stretched. Most of them have high melting points and high boiling points. Most of them need to be heated to well over 1,000 degrees to melt. There are a few metals that melt at lower temperatures, but the vast majority have high melting points. So let's define what some of these terms are. Malleability is the ability to be bent, twisted, or deformed. So gold is extremely malleable. Gold can be twisted and bent into virtually any shape you want. It can be pounded flat into a super thin gold foil. And that's one thing that makes gold really useful. And not only does it have its color and the fact that it stays shiny and doesn't tarnish, but because of its malleability, it was very useful for things like jewelry and ornamentation. Pounding it into that thin gold foil allows you to put it on the edges of books and to coat surfaces, to decorate them. In India, they even use gold foil for certain kinds of desserts as edible gold. It's not really digestible, it just passes through your gut and out the other side, but it does make the meal pretty. There are some metals that are more brittle and will fracture easily. You'll notice here on this piece of metal that if you try to bend it, it does snap. But most metals are pretty malleable, and that's useful for everything, from making pipes to chairs to fences to whatever. Ductile is related to malleability, but they don't necessarily always go exactly together. But ductility is the ability to stretch something out like into a wire. And so as you can see in this picture, this gum is very ductile. It can be stretched quite easily. And so making wire out of metal is very useful because you can stretch it into this long wire and it conducts electricity. But why do metals have these properties, and why are they so consistent across all of the different transition metals? Let's talk a little bit about the reason. It has to do with what's called metallic bonding. So we've talked about ionic bonding, we've talked about covalent bonding. Now we're talking about a third kind of chemical bonding known as metallic bonding. So first of all, the metal cations, these positive metal ions, are arranged in a regular crystalline structure, as you can see here. Each metal may have its own unique crystalline structure. This one happens to be a cubic structure, but they will line up in a very crystalline structure. Then the d orbital electrons that are a layer down from the outermost s orbital are actually free to move around, and we call these delocalized because those d orbital electrons are not stuck to the atom that they're on, but actually can jump from one atom to another. And so over time they average out to being the number of electrons around it, but they are not stuck in position. They are free to move throughout the crystalline structure. This crystalline structure can be seen when you grow metal crystals. And so, for instance, these are bismuth crystals, and you can see that they grow in these regular kind of cubic patterns. One of the cool things about bismuth is that the way the crystals grow on the surface of other crystals causes light to reflect at different wavelengths at different angles, and so you get this beautiful rainbow array of colors, and it changes at the angle that you look at the crystal. Okay, so we say that these delocalized electrons are a sea of electrons. So it's basically these metal cations with all of these electrons shooting around in every direction all around it. So we say that these cations exist in a sea of electrons. The crystalline structure are the metal cations, and the electrons are basically free moving throughout that crystal. So let's talk about why metals are malleable. So we know that metals can easily be bent, and they can be bent back into their original position. So let's see what happens here. So let's say we were to strike a piece of metal, strike this crystalline structure with a large force, just as we're hitting this car with some kind of a force. When that happens, the metal cations will shift in position, but the electrons are able to freely move to adjust to the changes, such that there's always a neutral net charge, that the metal ions are always neutral in charge, and therefore you can keep shifting these metal cations in any direction you want, and the overall net charge remains neutral. That is not the same as what happens with an ionic crystal. So let's look at what happens with an ionic compound like salt. So ionic compounds tend to be very brittle, which means rather than being able to be shifted around and moved, when you strike them, they just break apart. So let's take a look here. So we've got a crystalline structure of positive and negative ions aligned in a regular pattern. Now what we're going to do is strike that ionic compound with a blow and shift where the ions are located. Now when we shift where the ions are located, now notice that instead of everything lined up alternating positive and negative charges, the positives are lined up with the positives and the negatives are lined up with the negatives, and now instead of being attracted to each other, those charges repel each other. And so basically the plane at which it was struck lines up in a repulsive manner and breaks off. And so we call those cleavage planes, the places where crystals can basically break off, and that makes ionic compounds brittle. If you strike them, they fall apart. If you strike a piece of metal, the cations shift, but the electrons are free to move to adjust to that, and so the charges remain neutral and it's able to maintain its shape. So why do metals conduct electricity? Well, again, it has to do with this sea of electrons. Electricity is just the movement of electrons. And so if you were to add electrons to one side of a piece of metal, so we add the electrons on this side, those electrons come in and just repel electrons that are within the sea. And so those new electrons coming in push the other electrons further through the crystal, and in fact, will push the last electrons out of the crystal, and you basically have a current of electrons entering and leaving the metal. And so it's the freedom of electrons to move from atom to atom and actually leave the crystal allows it to conduct electricity. Compounds that are not conductive of electricity, that's because the electrons are essentially trapped in position around an atom. So adding new electrons does not force them out of the atom, and so they don't conduct electricity. The end is no net result as far as the total number of electrons in the system, because just as many are leaving the crystal as are entering. All right, so why do metals conduct heat? Well, it's actually the same reason they conduct electricity. So when you begin heating up a piece of metal, on one end of it, the atoms get more and more kinetic energy. They start vibrating more frequently as they absorb that heat energy, and the electrons have more kinetic energy to move away from the atom that they were next to. And so as they move, they repel other electrons, and they get more energized, and they move, and you get a chain reaction in which the energy moves its way through the crystal, entering on one side, leaving on the other, and so it's conducting that energy, it's conducting that heat. Metals tend to have pretty high melting points. For instance, iron doesn't melt till it's about 1200 degrees Celsius. As you look at this table here, you'll see the temperatures that these different metals melt at. They're pretty high temperatures. You have to get them pretty dang hot. There are a few exceptions to that. Zinc has a pretty low melting point at only about 787 degrees Fahrenheit. Now, that is not super cool, but it is cool enough that you can actually melt zinc on a stovetop. So if you were to actually place a penny, which is 95% zinc, onto a frying pan and put it on your stovetop, it would melt. The zinc inside would melt. The copper doesn't, because the copper's temperature of melting is so high that's well beyond what a stovetop can generate. In a campfire, you can melt zinc. You can, in a very hot campfire, melt aluminum, but typically your campfire will not get that hot unless it's really roaring. All these other metals are not going to be able to melt in there. You throw metal in there, it's still going to be there as a solid at the end. The highest melting point of any metal on Earth is tungsten. Tungsten's melting point is 3,400 degrees Celsius. So you'll notice down here, tungsten is W on the periodic table. It has the highest melting point. That actually makes it pretty useful for incandescent light bulbs, because the idea with an incandescent light bulb is you're heating up the metal to a temperature so high that it's releasing all of this light energy in black box radiation. But you don't want the filament to melt, because then you won't have the electrical connection to conduct the current. And so by using tungsten, it can heat up to 3,000 degrees, generate an enormous amount of light without melting. Tungsten is used in not just those incandescent bulbs, but in all sorts of high temperature applications in technology and industry where you don't want the metal to melt. To summarize, I have a video that goes over metallic bonding I'd like you to check out.